Hello everyone, and welcome to this lecture titled Power in DC Resistor Circuits. Up until this point we've been doing calculations around voltage, current and resistance, but we've been missing one key calculation or one key characteristic which is known as power. And as you'll see, it's very important to think about power in our circuits. So it's got here, power is an important property within electronics because when you are designing a circuit you will need to choose components that can handle the amount of power that your circuit requires it to. And let's run through an example and then we'll watch a little video clip, and surprise surprise, I am in the video clip. So what I've got here is an LED. Now I'm not going to cover this properly at the moment, but an LED is a special light. In fact, it's a light-emitting diode. It's got two connections, and at the moment let's just call this a 2-volt LED. That means when we connect it into the circuit like this, the LED will have 2 volts across it. If we start with a 12-volt power supply, our resistor is going to get 10 volts. So again, there's a whole heap of theory going around LEDs. It's a semiconductor device, and it has a forward voltage drop and all these different things. But at the moment, just know that it's going to give off light when we connect it in the circuit, and it's going to get 2 volts of that 12 volts. So if we were to calculate the current going through this circuit, it's a simple series circuit. All we need to do is figure out the current through the resistor, and that tells us the current through the whole circuit because it's in series. So how do we get current? Well, we need voltage and we need resistance. So current equals V on R. So current in the circuit, which is the current through R1, same thing, equals 10 volts divided by 33 ohms. And what do we get? 10 volts divided by 33 ohms, and we're looking at, so 0.303, which is around about 300 milliamps, but 303 milliamps. So that's what I want to design with my circuit. I want this LED to shine nice and bright, a really, really bright LED. To do that, I need lots of current to flow through it. To get lots of current, I need a resistor that is a really low value, in this case 33 ohms. And so if I connect that circuit up, then I'm going to get a nice bright LED. So let's connect it up and see what actually happens in our circuit. Alright, so now we can actually start to construct this circuit. So as you can see on the screen, we've worked out that we need a 12-volt power supply here, or we've got a 12-volt power supply coming in, positive at the top, negative down the bottom. I've got my multimeter, so I can actually double check that my power supply is set to 12 volts. I've then got my circuitry here. Here's my high-powered LED, so that's going to be nice and bright. And here's my 33 ohm resistor. So remember, as we did the calculations, there's going to be 10 volts across the resistor because the LED gets 2. 12 volts take away 2 leaves us with the 10 for the resistor, and we get about our 300 milliamps because of that. So this is going to be great. First of all, I'm going to check the multimeter leads are working, put it to ohms, and connect these together. Looking at less than 1 ohm. Oh, I missed it. Yep, so that seems good. Now I'm going to check the power supply voltage. So my negative connection goes down here, and my positive connection goes up here, and what do we got? We have, let's plug in the power supply first of all. Very good, 12 volts. So there's my 12 volt power supply. Let's connect up the resistor. So as you can see the circuit on the screen over here, we've got 33 ohms connected from ground, my negative connection, up to here. And then we just finish off the circuit with this LED. So remember, we're going to cover LEDs in a later module or a later course or something like that. But basically the long lead is the positive, the short lead is the negative. So we just need to make sure we get that correct. If we get it wrong, I'll just show you. If we get it the wrong way around, so the short lead to the positive, the long lead to the negative, you can see the LED just doesn't work. So we have to get it the right way around. Okay, so let's see what happens with this circuit, see if it works. Ah, very good. The LED is shining nice and bright, which is exactly what we wanted it to do. And hang on a second. What is happening here? Oh, that's all bad. What is going on there? I'll just turn off the power supply. Oh, I don't think that resistor... Oh, that is very hot. That is very hot. What is going on? Now, why did that resistor turn black? Well, there's a very good reason this resistor turned black, and let's go through the calculations to figure that out. Alright, so that was a little bit interesting. We found that we had a 12 volt power supply. That was all good. We found we had an LED, a nice red LED. It was going to get 2 volts of that 12, and then we had a 33 ohm resistor right here. All of that put together gave us a current of around about 300 milliamps, as you can see here. But what actually happened to the resistor? The resistor burnt out. So you could see that smoke was literally coming out of that thing. It was getting so hot it could not handle what we were trying to make it handle, and that's what I'm talking about up here. Power is an important property within electronics, because when you're designing a circuit, you will need to choose components that can handle the amount of power that your circuit requires it to. So how do we get power? Well, have a look here. Power is the rate at which work is being done, and in our DC circuits we can calculate power in a number of ways, and here's 3 ways that we can calculate power. So I've got up here as well, power is given the letter P and is measured in watts. Watts we just abbreviate to the letter W. So I'll tell you right now, this 33 ohm resistor that I was using, if we were to look this up on the internet, if we wanted to go to say DigiKey or Mouser or eBay or whatever electronic store to buy our resistors, we could actually get some information about the resistors. One of the characteristics we're going to get is the maximum power capability. This particular resistor I was using was classified as a quarter, oh, it's not right there, there's no room. It's classified as a quarter watt resistor. So what does that mean? Well, a quarter watt, 1 divided by 4, is 0.25 of a watt, which is, another way to say that is, so you got 0.25 watts, which is 250 milliwatts. So that means this particular resistor that I bought and put into that circuit can handle a maximum of 250 milliwatts. But how much power were we trying to make it handle? Well, we can calculate that in a number of ways. We can do power equals voltage times current. We can do power equals current squared times resistance, or power equals voltage squared divided by resistance. Let's just go with this nice easy one right here. Power equals voltage times current. So I'm going to copy that and paste it in over here. Let's put it up there, and we don't need this anymore. Let's put in some values. So power equals voltage times current. What's the voltage across that resistor? It's 10 volts. So power equals 10 volts. What's the current going through it? 303 milliamps. Put that into the calculator. 10 volts multiplied by 303 exponential negative 3 to give us milliamps, 3.03. And that's given in watts. How much could this resistor actually handle? What is it rated at? Well, let's go back here. I said it was a quarter watt. It can handle 250 milliwatts, so nowhere even near 1 watt. But we put it into a circuit where we were saying, hey, I need you to be able to handle 3.03 watts. There was no way that this guy was going to be able to handle it, and that's why you saw it actually literally smoking. And if I had to let it keep going, it may have actually literally broken, actually split apart. So what is this thing that I'm holding? Well, you would have seen this in a previous lecture. This one here is another resistor, but it's a higher power resistor. This one here is 5W. This can handle 5 watts. This one can handle a quarter of a watt. Notice the size difference. The greater power rating a resistor has, generally the bigger it is, because it's expected to be able to handle or dissipate a lot of heat. So in this case, the resistor that I need in there is going to need to be at least 3.03 watts. So if I was to put in a 5 watt resistor in there, that would be perfectly fine. But a quarter watt resistor is not fine. In fact, we destroyed the thing. So there's other ways of finding power. We can use I squared times R. Let's just say that we did not have voltage. Let's say that we had no clue what the voltage was across this resistor. All we knew was that it had 303 milliamps going through it, and it was 33 ohms. Oops. We could use that information here. We could go power equals 303 milliamps squared, there's our I squared, times the resistance, which was 33 ohms. put that into our calculator. 303 milli squared multiplied by 33 ohms, and there's our and we'd round that up to 3.03. So we get the same answer, 3.03 watts. What about this one, V squared on R? Let's just say that we did know the voltage, but we did not know the amount of current. So we knew it had 10 volts and it was 33 ohms. In this case, we would go 10 volts squared divided by 33 ohms. What does that equal? Well, 10 squared divided by 33 is 3.03 watts. So all different ways that we can calculate power. So I guess the key thing to take from this is, if you're going to be designing circuits, and I guess I wouldn't really be doing this course if I didn't want you to be able to design circuits, you need to have a little bit of a think about the power requirements. So if you're going to design a circuit which has so many volts across a resistor and so much current going through that resistor, you just have to figure out, well, what is the power that this thing requires to be able to handle. So you go, well, this thing needs to be able to handle, let's just pretend we came up with a value of, say, 225 milliwatts, let's say. So you've done the calculation, you go 225 milliwatts. Well, in this case, the quarter watt would be fine, because a quarter watt can handle 250 milliwatts. But if we were to do a calculation and we found that it needs to handle, let's say, 328 milliwatts, a quarter watt resistor is no longer any good. You would have to go to the next size up, which is a half watt, which is 500 milliwatts. Above that is 1 watt, and then you might go to 2 watts and 5 watts and 10 watts. So we have all of these different resistors that can handle different amounts of power. And it's not just resistors as well. The same applies for LEDs, and we have capacitors and inductors and other components like that that have a maximum power capability. Alright, so hopefully this lecture on power has been helpful, and I guess that's it for now, and go enjoy your questions. Thank you, guys.